This is the demonstration for the deployed genetic algorithms program. So as we can see here, these are the code files. We are having this, and these are the this is the data file which I will be showing what it is, and the others are the result files. So let's run the greedy program first. So as we can see, it's a 354 line of code program. So it's already compiled. So just let's run it. So as we can see, it is the interface on command prompt. So here we are having the three options. Press 1 for giving data yourself, press 2 for creating the random country, and press 3 for the default data. So let's keep the data default here, and in the others we will be having a random country. So let's press 3. So here is the data for the here is the default data. So as we can see here, it's the data from the 12 cities of Indian country. Cities names are here, and these are the distance chart, and the other is the dynamic cost chart. It's randomly generated here, but in the real time we can obviously use the machine learning concepts and other factors, the linear regression concepts to find this cost. So it's again now asking us the salesman city. So let's keep it any between 0 to 11. So let's keep it 4. So now we have to press S to show the results. So these are the final results. Like here are the 10 greedy solutions. So the greedy approach is simple. Like we go to each city and see the city which is having the least cost, and we go to that. So these are the 10 greedy solutions here. So here below we are having the average of the 10 solutions. It is 936, and the deviation in the variance is 2787. It's a large value. So let's compare it with the other ones. So the next program is SGA, the simple genetic algorithms. It's again a long code, long LOC. Here the LOC is 643. It's already compiled. So let's run it. So now here let's go for the random country. Now I will press 2. So like it has generated a value for us. Like it is saying that there are 16 cities numbered 0 to 15, and now it is asking us to continue or to change the number of cities. So let's change the number of cities to a small value. Let's keep it 7. So this is a randomly generated country which is having the distance chart as this and the dynamic cost chart as this. Let's select the salesman city. Let's keep it 3. Now it is asking us the how many chromosomes in the initial population. So for genetic algorithms we need to provide the initial chromosomes values, and here it is written that for quick results we have to keep the value between 8 to 40, and for the better results we have to keep the value to 40 to 1000. So let's keep it 100 to check what happens. So now it's processing. The processing is done. So now we are having we have to press S to show the results, or we can press E to see the detailed results. So let's press E here, and like let's maximize it. So here are the top 10 fittest individuals which we got. These are shown as like this. You can see that the different paths are having the different distances. So like the average dynamic cost is here 547, and we can see that the variance has decreased a lot. Like from 2700 it has come to 243 now, and here is the value. Like there are 1160, approximately 1160 individuals in the final population, and out of the all results the most optimized solution is shown here. Like it's from 3 to 4, 4 to 0, and so on to 2 to 3. This is having the total distance this and the dynamic cost this. So this will be the path return after the algorithm. So now let's check the final algorithm, the deployed genetic algorithm. As you can see, this is the code. It's again a long code. It's having an LOC of 919. It's again already compiled. So let's run it. This is the DGA. We will be again creating a random country or the random city only. So let's press 2. The return number is 8, so just let's continue with it. This is the distance chart and the dynamic cost chart. Now the salesman city, let's keep it 6. Now let's keep the initial population to, let's increase the value, let's keep it 400. So it's processing, it's done. Now let's again see the detailed results. So these are the detailed results. So like in the deployed genetic algorithms, we are not having a single path, we are having the genotypes and the phenopath. So basically these are the two genopaths and this is the phenopath. Like basically the result is this one and the distance is this, the dynamic cost is this. So as we can see, like these are the most optimized solutions. Now the average is 677 and the deviation is 348 here. So like for this particular case, the deviation has increased from SGA, but as I have done, as I have shown in the results, I have experimented on different values. So the deviation of the, and the other reason of different deviation is here also, like I have kept the countries different. If I have done the same manipulations on the same data, the deviations results would have been different. Here the deviation is 348 and the total individuals are 7451. So for this particular country, the most optimized solution will be this, and which is having the 34800 unit total distance, and the dynamic cost is 712. So like you can go through the result section and check like for different graph sizes how the results are varying, and in the more of the cases the deployed genetic algorithm is the most optimized solution, giving us the most optimized solution. So like let's check that once. So it's in the result section, it's the conclusion. So for graph size, the greedy approaches for the 10 tests is this, which is this average. Now the simple genetic algorithms for 10 test cases is this, and for deployed it's this. So for different graph sizes, the results are this. So this is our final result. So after you will go through these results in the below sections, you will be able to see that we can conclude that DGA is better than SGA, and they both are far better than the greedy approach. Also, with increase in size of graph performance of both DGA and SGA goes down. So, thank you.